Frank. We're talking about AI, and welcome back everyone to Merge Conflict, your weekly developer podcast. If you're brand new here, jam that subscribe button, hit like or hit follow or give us a review, whatever you want to do. Just follow this podcast because this is now the official, unofficial, sometimes on occasion, we talk about AI. And today we're talking about everyone's favorite topic, Frank, tokens. Ding, 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 ding,
Tokens?
Ding. Yeah,
tokens?
It's like, okay, here's how I describe tokens. It's like this. It's like when you go, no, I'm done doing it. It's like,
okay,
you go into the boardwalk, right? There's all of these games, okay? All these games, okay, that are out there.
Okay.
And you go and you take your money. You take money and you put it into the machine. It gives you a bunch of tokens. So there's a currency from like $1 to 100 tokens.
Yes.
And then each machine model has an input of how many tokens are needed to put in, the limit, the limit of tokens that you can put in to play. Now, often on this scenario, which is it's all wrong, by the way.
It's the worst analogy I've heard. And I think your
like,
analogy is wrong too. Can I just have to interrupt? It's wrong. The machines give you tickets. The machine gives you tickets. You put tokens.
You put in tokens, yeah.
Tickets come out. So what this has absolutely nothing to do with.
No, it doesn't.
TikTok. Is that what we're talking about?
No. Okay. We're talking about tokenizers, tokenization. We're talking about Claudes and Geminis and GPTs. I don't know. I watch a Fireship video and like every 5 seconds it's something new.
This is crazy. Okay. I think we almost have to apologize for this episode. We just got into a discussion about tokens and tokenization and what does it really mean to be a token in an AI networking world? Yeah. And somehow it's bled over to a podcast. So hi everyone. Let's just talk about some fundamentals of AI here. Because why not? It's like the most overused word at this point. I don't think it's entered like the common vernacular. I haven't heard like any of my cousins saying tokens, but like you just spontaneously started talking about tokens today. So like this isn't even my fault. This is on you.
Now, we've talked about tokens on previous episodes of the podcast. And when Frank was talking about it, I didn't really know what he was talking about. That's really what was happening. But now I almost know what he's talking about.
Do you? Okay, cool. Yeah, so tokens have become the currency of AI. So with the dawn of the large language models, the LLMs, the oracles from on high, our great overlords, are we talking into the future?
Sure.
We got to be nice to the robots.
Yes.
They all work with text. Isn't that weird? Like, who would have thought we would do a whole episode on consoles and how to make console apps good in this modern world? And then this week, we're going to talk about tokens, which, by the way, tokens are just text. They're just a funny way to represent text. FYI, I'm just cutting through 30 minutes of this episode and just getting to the end. Tokens are text. There's a simple transformation. It's not that simple. But their tokens are just text.
Aren't they really numbers though?
Okay. We assign them numbers, okay?
Yes. I win 1-0, baby. That's right.
Is the letter A a number? Well, in ASCII it is. In Unicode it is. You know, you can assign numbers to anything. Anything that you can enumerate, anything that you can list. We're programmers here. We know this. Anything that you can make into a collection, you can assign a number to. So yes, they're numbers, but they're numbers in two forms. So when you see a token, they're usually an integer because there will be a vocabulary, and we can get into what that actually means. But a neural network, I'm going to throw out numbers that are probably wrong. You can look up the real correct numbers, but like a network like GPT-3, an older network, I think it had something like 50,000 different tokens.
That's correct. Yes, 52,000. I'm pretty sure.
Plus is that 52,000? Yeah. Thank you for looking that up.
Yeah, I just know off the top of my head. I was side tangent. I was in Fred Meyer's the other day, and we were buying some firewood, and the firewood has like I got the axe thingy. It's amazing. It has
You
the
did?
tiniest
Thank
part.
you.
It's amazing. It's so good. So it has like the tiniest barcode in the entire world on it, and it doesn't
Yeah.
scan. So this guy comes over at the self checkout, and from memory types in this 20-digit code. Anyways, that's
God.
my assimilation with this wood has
Yeah.
numbers associated with. Basically, they're
Everything
UPC
does.
codes. Everything's a
Exactly.
UPC code. Oh
Yeah.
my gosh.
But it's a serial system because yeah. Um, but like those numbers are arbitrary, right? Like we could put them in any order and all that stuff. So there's a lot of things we could talk about with tokens. We can talk about like why do we tokenize at all? If we're writing English sentences, you need the letters of the alphabet, the space character, the period, question mark, one or two emojis. You really don't need it. You could really just use individual characters and things like
Well,
that. So we could talk
then
about why
why
even
do we
tokens.
tokenize? Why, Frank? You prompted it. Let me ask it.
Uh,
Why do we
okay.
use tokens? Why can't I just send in the text?
Compression.
Mm.
We use tokens because this is jumping ahead a little bit, but all these neural networks that we're inputting all this text into, all this data into, that has to go into a buffer that a neural network can understand. And the way we design these things, that buffer's got a fixed size. Or what I should say is it has a maximum size.
Mm.
And we often call that the context size of these networks. And that's what it is. But the context also includes your history, the system prompt, and your current prompt. So the history becomes the bulk of it, but there's a lot there. And that's a fixed size. And if you take a 1,000 character sentence, how many tokens would that turn into if you don't have compression? It would turn into 1,000
1,000.
tokens.
Yeah.
But we all know the English language repeats itself a lot. We use some character combinations and we don't use others. So someone one day got a very clever idea in their head, and they're like, what if we write a little compressor that figures out the most common combination of 2 characters, the most common combination of 3 characters, the most common combination of 4 characters. And we come up with a fancy way. People love writing compression algorithms. Programmers love this stuff. Computer scientists live on it. They write books on compression algorithms. So there's a million ways that we know how to do this. And the compression algorithm people came up with is called this tokenization idea, where you find substrings that just occur very often in the source text. So the word the, if you have 1,000 words of English, the word the is probably going to be in there a couple times. So you might as well just assign the whole word the into one token. And now you have a compression of 4-to-1.
Yeah.
And the compression is usually not that good, but it's good enough. So in the case where I would need 1,000 neural network entries to represent 1,000 character sentence, now I only need 250, and the network can run a lot faster. That's one aspect, but there's multiple. But I should take a pause because I just said a lot of words.
No, I think that makes sense to me 100%. I think one way of looking at this that's really helpful, by the way, is to go to platform.openai.com/tokenizer. I'll put it in the show notes. Mm-hmm. And what this does is it does give you a brief overview of how OpenAI's LLMs, GPTs, process text using tokens. So its definition, we'll see how close it is, which are common sequences of characters found in a set of text. The models learn to understand the statistical relationship between these tokens and excel at producing the next token in a sequence of tokens. So it's just tokens followed by tokens, and those tokens refer to something. Now, the cool part about this is that you can actually enter into a open text box, and it will show you the characters and also the tokens that are there. So for example, if I say hello world, that is 2 tokens, 11 characters. If I say hello, I guess hello Frank.
I said hello
world.
James.
Yeah.
So right. So this is the beauty of the compression. The word hello comes up a lot in English. So they have one token represents the entire word hello. And then I put in James, and James comes up a lot, I guess, in English because James is
Mm-hmm.
an entire single token also. And so, like all compression, it's just a heuristic. They just collect a bunch of statistics. You actually train the tokenizer. Like when I'm doing my cuneiform work, I'm training tokenizers to look at a bunch of text and figure out what are the common patterns and take those
Yeah.
common patterns and merge them into a single token and keep doing that, keep doing that, keep doing that until you get maximum compression. So when I gave the example of the word that was a 4-to-1 compression, but James, hello James was 11 characters down to 2 tokens. So that's 11 to 2 compression or 5.5 to 1 compression. Pretty
And
great.
here's another good example is we just did a Patreon exclusive half an hour video and podcast, basically. If you want more of us,
Yeah. Yeah.
patreon.com/merchant.fm. Shout out. We have Patreon, but bonus episodes every week. It was called AI Kitty Litter Box. 4 words, AI, that's one kind of. Kitty Litter Box. AI token. Kitty
Yeah.
token. Litter,
Nice.
2 tokens.
Litter. Not
Litter
common
is
enough.
not in there. So actually L is its own token and then iter apparently. But
A lot
because
of itters out there. Yep.
a lot of iters, most likely litter is down ranked compared to other iters. So it's able to,
Yeah.
it makes that trade off, right? Instead of putting all of the iters in there, boom, and then box is another token. So that's really cool. So like, that's a good example. I was just trying to find something that wasn't just
Okay.
a 1-to-1 with words that, because then, it's every word that's in there, but not every word is in there. We have more than 52,000 words.
Now, I want to give one more good thing about tokenization and one more bad thing about tokenization. You want the good news first or the bad news?
Bad news. Heather's.
Oh,
I've been
really?
saying good news. I've been saying
Wow.
good news, bad news with Heather, and she's just like, "Give me the bad news." And I was like, oh,
You're
like the
such
good
a
news isn't that
okay.
good. That's why I said the good news isn't
This
that
is
good.
Heather's doing. Okay.
Yeah, it is. It is. Yeah, it is.
See, I thought you were going to be more positive. I really thought you were going to go for the positive one there. All right,
Nope.
the bad news. Try numbers.
Mm.
Numbers don't do well with tokenization. So if you think about what I just said, um, what things become tokens? Common strings in,
Yeah.
let's say, English, and they do try to train these things multinational, but multi-language, I should say, but they're really the big ones are really English dominant right now.
Yeah.
Anyway, numbers are a bad example because what is the difference between 1.0, 1, 1.00, 1.00000000001? You know,
Mm.
these all
No.
conceptually to a human being thinking person that knows anything about any kind of numbers, these are all roughly the same thing, that number. But those are all have very different tokenizations to the neural network.
Yeah.
So the concept of the number 1, you would think is a unified general concept. The tokenizer can really mess with it. The tokenizer can really influence what the network's able to learn because now the network can't just look at one token and know, oh, that's the number 1. It now has to learn 50 different tokens. I mean, literally a million different tokens can actually be combinations thereof, can actually be the number 1. And they're all just as valid. The number 1 with a million zeros behind it is still the number 1.
Yeah.
So that's unfortunate. It's wasted space in the neural
Mm.
network. It's so a lot of the reputation that these language models get is that they're bad at math.
Yeah.
And 50% to 90% of them being bad at math is because of the tokenizer,
That makes sense. Yeah.
because
Just,
the way it represents numbers is not ideal.
yeah. I typed in a lot. It seems like it also maxes out at 3, at least in this tokenizer example,
Mm-hmm.
it max out as like 3. So if I do 0, 0, if I do 0, 1 token, if I do 0, 0, 2, 1 token, if I do 0, 0, 0, 1 token, if I do 0, 0, 0, 0, 2 tokens, it's like the max is 3
Yeah.
basically is what it seems like. And then, yeah, if you do, that's the other part is if you do 1.0, that's going to be 3 tokens because it's 1.0 and then another 0, it continues in this way with that. So it does become a pretty lackluster experience. So that makes sense. Yeah.
And it's a difficult problem because 1.1, that could be the number 1 and 1/10, or that could be section 1.1. So
oof.
Text is not a great input. It's, history has a sense of humor. And it's funny that text, we all wanted natural language input. It's been the goal of machine learning AI forever. But turns out natural language is not that great at some things. Numbers and being specific about objectiveness of things. A lot is just gleaned from context. So there's not a great way to represent 1.1. It could be a number, especially at the tokenizer level. You just don't know. So they play it safe usually. That one might even be a token. That one comes up, but you can imagine a lot of numbers that come up and a lot of other numbers that never do.
That makes sense. I like that. So these tokens all have numbers assigned to them, right? So the words are tokens, and those tokens are assigned to it basically.
Substrings, really, technically. Yeah, it's not words. For the common words, it's a word, but really just think of it as a substring of all the text in the human world here.
So what do we do with these tokens? Like, I mean, if I have a bunch of things.
Are you ready, James?
Tokens. I'm ready. Yeah. What do I do with these tokens?
Are you ready for the good news? Because you didn't want the good news before.
Do I get tickets back? Yeah. What's the good part?
No, you don't get.
Am I cashing this in for a prize at the end of the day?
No. Okay. Well, there's 2 parts to the good news, but I'll start really high level. The neat thing about tokenization is that, like, the concept of the word "the" THE in English, it's nebulous, but it comes up. It means a lot of things in a lot of contexts. And that becomes a single token. And so the network can learn a lot about that token. It's kind of the opposite of the number problem. See, I really thought you were going to go for the positive first, and I had a great segue. Like, here's a good thing, and then here's how that good thing falls apart with the numbers.
Yeah.
It's the opposite of the numbers. The problem with numbers is there's a million ways to represent the number 1. But there's one way to represent the word "the." It's the word "the." And so the network can learn a lot. And it can get really good at using the word "the." There's a word going around that if you see it in generated text, or if you see it in text, it's probably an AI generated, because it just favors some words. It got good at some words, and it likes some words. And I really can't remember it. I think it was like an adverb or something overly. Anyway. So it becomes really good at the word "the," and it becomes really good at other words that become a little annoying that it keeps repeating, just because it has a lot of information about those words.
That makes sense. It makes a lot of sense. Yeah, because those tokens and those words are going to be used over and over again, and it can infer a lot by the surrounding parts of it as well, I assume, in the learning process.
Ready for good news part 2?
Yeah, I'm ready for great news part 2. Let's hit me. I'm ready.
Okay, so we took all of English text, broke it up into tokens.
Yes.
Boom. We assign numbers to them. Completely irrelevant. And we just, the number 42 is some token. Yeah. We just, because we need to. We're programmers. We got to put this stuff in an array. They got to have some order when they go in the array. So we assign numbers to them. That's really the whole reason why. It does not matter. What does matter is these fancy networks learn another number, a more advanced number, a tensor, some would say, an embedding, others would say. So for every single token, a thing called an embedding is learned. So this actually has information associated with it, information that only the neural network really knows how to interpret. But it's information that it chose to learn during its training process. Sorry, I'm giving it a lot of animus, but in my mind, these networks are, they're doing their own thing. Yeah.
Yeah.
So we get this thing called an embedding. And it turns out we have learned how to do very interesting things with these embeddings because they are information packed. Basically, the networks have learned to just, oh, in the olden days, there were always interesting things about the embeddings. Like if you took the embedding for the word token king or the couple tokens king, whatever, just make your array longer, and you subtracted man from it, you would get queen. So like it learned this fun arithmetic that it could do over these. We used to call them word vectors. Now they're called embeddings because they're not quite linear the way they used to be linear. Those were called variational, but whatever. But they still have a lot of meaning like that, and we can do fancy things. And you were telling me about a project you did with fancy things with it, but I think that's what's really neat about these tokens is once you have a network trained on them, now all of a sudden there is actually this chunk of information that's tricky to interpret, but it's associated with each token.
Yeah. And how I've watched a few YouTube videos. I spoke with several people, and I've been doing a lot of reading. Often you'll see it described in the simplest terms as XYZ. Think of we as humans can understand XYZ coordinate system, right? We mostly can understand an X and a Y. Z is a little complicated, but Z is the depth. So
as long as your eyes are working, yeah.
Yeah. So my understanding is you take the example of the king, but you also have something of queen, and you have XYZs that are kind of pointed in a direction. They're kind of pointed, and maybe, for example, king and queen are on different because how the machine learning did is like, well, these things are very different, but they might be in some direction because they might say, oh, well, king and queen, how they are, they're of some timeline or something like that of days of yore, right? Of castles and whatever, right? So they might be somewhere just like a woman or man or aunt and uncle, right? And the idea is that most likely things that are really relevant. So like you were saying, there might be king and man, and over here there's queen and princess, and all these other things that are in the similar vein. They're probably pointing in very similar directions, which means if you subtract that, like you're saying, you will probably find those things, basically the distances between them. Yeah.
And that's my favorite metaphor, actually, because it's honestly really close to what's really going on, even at the math level, at the if you're implementing these things from scratch with code, it's really close to what's happening. So in your case, you're saying the XYZ, that's 3 dimensions, so that would be 3 numbers that you would associate with each token. And those 3 numbers not combined, just listed out, the 3 numbers, that would be the embedding for the token. And then if you have a whole bunch of text, the embedding for that text is all the numbers just stringed out one after another. And I love that analogy so much because we do talk about these things as dimensions in code. Yeah. It's a metaphor itself, but in code, it's called a dimension. I was programming them today. And the only difference is, in your example, there were 3 dimensions. And in the case of something like GPTs, I mean, there's 700, 1,000, So it is a 1,000-dimensional space out there where nebulous concepts can locate them. Or these aren't fully concepts because there's more concepts in the network, but information. It's almost like a database.
Yeah, it is. And it's doing these lookups in general. I'll put a link to the one video from 3 Blue 1 Brown, which is what is a GPT. And he often uses that very similar metaphor, and he does really fun stuff with it. I don't know if I can actually look at it is any ads and whatnot as it's going through, of course, but there's a whole series basically that he has. So he has one that's like, imagine you put in king, and then there was another one that was like lived in Scotland, right? And those are 2 things that are pointed. And then it's like, okay, well, that actually would end up basically, there's like another one that points to murdered predecessor, like in Shakespearean language. So it's like building up this. So the idea is this, right? Was he gave it a prompt of the king doth wake tonight and takes his ruse or whatever. And it's like kind of building out this, and then it ends up pointing to, these arrows in this XYZ can do the same thing but in a different era, basically, is it's able to look up a similar king or queen or whatever it is, and you could change it to queen, and then it would follow a similar path, basically. I'm doing a bad job of explaining what's going on, but it's a great video.
Well,
that's all I'm
you're
saying.
you're creeping into how the networks actually work themselves. So
Yeah.
if we're drawing lines at layers, everything I just said is basically all that exists with tokens at the token layer. Tokens take text, compress it down. Those compressed versions of the text get some kind of data associated with them, called the embedding. After that, now more interesting things start to happen with these language models. They have the transformer attention mechanism for every token in the input. It looks at every other token in the context.
Mm-hmm.
And it starts comparing and contrasting, calculating, doing crazy matrix math, doing neural network stuff. And it's fun after that. So that box is really big and hard to investigate, but what it really is doing is just finding associations between words in order to predict the next word. But finding this elaborate network of associations that you're walking through when you're talking about this arrow points to that. It's all these associations that it figures out to output its answer, which is quite vast and takes a lot of CPU time to do.
He had another one which was showing, and this is a better example, but like imagine Germany and Japan, and if you had like Japan plus sushi, so you have Germany, Japan, and sushi, and there's basically like those in there. And what you could do is like draw the distance from, if you're in a 3D space, from Japan to sushi.
Mm-hmm.
If you did that same arrow from Germany up, it actually points at bratwurst.
Yep.
Great example, right?
Yeah, that's where sorry. You just pointed out where I made a mistake with my analogy when I said king minus man. I knew I was doing that wrong because you want to find a delta that you already know. You want to find an arrow, a delta, and then you want to apply it to a different location just to see what kind of answers it would come up with.
Exactly.
And it's a fun way to navigate the database that's created out of all of this, because in the end you want to query the network itself. That's the interesting thing, where it generates new answers. But just this whole tokenization and embedding process, the process of it learning, associates all this interesting data with the tokens themselves.
Yeah, it's very, very fancy and really interesting to think about. And this video does a great job, and hopefully you've done a little bit of a good job, I think, of just a little bit of the video, just kind of talking through it. Because I do think that end part is very fascinating. The guessing of the next word based on the embeddings and the numbers. There's all these pluses and minuses that go into it, and then each of these different models also have like a temperature associated with it as well, because there's all sorts of things. Is there might be, if you had 0 in the temperature, basically there's the weights. It's basically the temperature is the weighting, and it, right? Or no?
It's the amount of randomness.
Sorry. Okay. So there's weighting already, but the amount of randomness that would go into the weighting, and it allows it to kind of have a little bit of fun. And he gives a good example, is like, imagine you started typing "once upon a time there was a," right? And it would say,
you want a random answer, or do you want the most predictable possible thing?
Exactly.
Now, if you are working at work and you're querying the company database, you want the most accurate, predictable answer. But if you are brainstorming, you want some craziness in your life. You want a high temperature. Let's boil that pot, see what comes out.
Exactly. And in fact, if you go in to, let's say, Copilot, like on your Windows machine or Bing Chat, there is the more creative, more balanced, more precise. And now I understand what the heck that thing is doing. Is just slightly adjusting the temperature.
For the record, we have literally talked about that on this podcast, but great. I'm glad it's sinking in. We're getting it into you.
Frank, now I understand a little bit. Just a little bit.
So this is a good chance to, let's rewind a tiny bit and do the layers one more time, just because you jumped up to layer 3. Layer 1, we take text, turn it into tokens. This is the most basic layer. This is mostly what we talked about. Layer 2, a lot of magic happens. This is the generative prediction model. It takes those tokens, decides what token is going to come next. That is the AI in the AI. Okay. So that's level 2, let's call it. Level 3 is it outputs a bunch of probabilities. What you do with those probabilities, if someone said to you, you have a 90% chance of winning $1 million with a 10% chance of dying tomorrow, do you take it? So like probabilities, they're tricky things. They're not always obvious. But anyway, this thing's going to output a probability. So we have to decide what we're going to do with those probabilities. And that's what you were talking about with the temperature. When it's a high temperature, you're feeling saucy. If something's low probability, you're like, let's do it anyway.
Yeah.
When you're low temperature, you're a little cold. Analogy really breaks down. You just want the most successful, the most optimistic result coming out of the thing. So 3 layers: tokenization, magic, sampling the probabilities. Those are the 3 layers.
There you go. I'll link to this video that does a better job of me getting in the way of Frank explaining it in more detail. That's good. I think what's nice is if you're listening to this, it's a little, again, hopefully it wasn't too hard to follow, maybe a little bit hard, but I do recommend watching this video as well. Like I said, I'll put it in the show notes because it's all visual. And I think that's what's been helpful is that when you and I talk about it, and I didn't understand it. So actually, if you've made it to the end, what I'd recommend is go watch this video and then go listen to this podcast again. And that might be a good place to start, because I think the visualization helped me better understand. It's like, oh, when you mean a token, what does that mean, right? To actually see the number. Oh, when you mean an embedding, what are the numbers that are there, right? To get some visualization. And obviously you can't visualize the entire, like you said, coordinate system. And it even makes a joke. It's like, it's like literally impossible for us to even fathom a 10,000 coordinate system. You know what I mean? It just, you can't do it. But he kind of like, goes through it. And I think the arrow pointing stuff is really, really spot on. Yeah.
Yeah. And it's a tricky one because the tokenization is taken a little bit for granted these days. People in the ML world, we don't talk about it much. Like it's something we all suffer through because we acknowledge it needs to happen, but we don't like to talk about it. So you'll get fewer nice introduction videos on it and things like that. So it's kind of fun that we spent some time talking about the low level feature.
Yeah.
But yeah, these things are a real deep dive. And I do have to say, if you're interested in how these things work and you can handle reading a research paper, I know small font, they can be quite obnoxious sometimes, but there is a research paper called Attention is All You Need. And it's kind of what set this architecture afloat. And in it, you're talking about visual explanations, is a graphic showing how the transformer network works. And in my head, I always reference that graphic. Even during our conversation today, I always had that graphic up in my head because it's just a nice little reference for me. So 3 blue, 20 browns. I'm sure they're great.
Yeah.
But I just want to give props to the original authors of the original paper because they wrote such a graphic that is stuck in my head.
Yeah. I think that's a good thing. If you have a link, I can shove it into the notes somewhere over here as well. I think sometimes
nice archive paper. Yeah.
Yeah. And I think that's the hardest part too, is a lot of times you're sort of thrown into when I watch demos of people doing things, like it's almost like, oh, I don't even know those basic words. And I know I don't know them 100% yet. And even this video that is not out yet, but will be out this Thursday that Frank was reviewing, is we were talking about it in our Patreon, is like, the reason I didn't even go further in that video is because like I don't feel comfortable 100% doing a tutorial on like what that is actually doing. You know what I mean? I enjoy talking about things that I actually understand at a high level, because I think that's one thing, is it's really easy to go to crawling to sprinting on this stuff. And sometimes you get into a session, you watch a video and they're already sprinting. And you're like, whoa. I don't know. And I get flack sometimes on that too. Is like, wow, James, why do you do so much beginner video stuff? Because I was like, one, that's what I'm good at. And also, I've never been sprinting when it comes to mobile development. I stopped at a run. I cannot run, that fast. I'm a runner, and that's it. I don't go any more than that. That's who I am. So that makes me really good at those, explaining those other layers. So anyways, these analogies are terrible. That's why I'm not a professional analogy maker, Frank.
No, I think you could probably make some big bucks, but you'll find another way.
I will find another way. All right, before we get out of here, we had a bunch of other exciting stuff we'll talk about next week. All sorts of Solution X files. We're back to XML.
XML, baby.
XML
forever.
That kind of makes sense. CS projects are already XML. It's fine. Frank says it's fine. Let's see if we got any questions on our YouTube. On the Spotify.
We're doing a free Q&A.
Yes. Yes.
It's
good
Q&A time.
Yes. I think the one we just got one feedback, which was on the Adobe Voice Enhancer. As I did learn my lesson, actually, is that on the audio version, the first time I ever did it, I took the finished track with the music and put it into the enhance, and that messed up the audio.
Made the music funny.
Yes.
Okay.
So
yes.
I didn't do that on the last episode. So Dunkel, give that a listen. Let me just double check a few things before we get out of here. Let's check the podcast episode comments. We got nothing. Perfect. Let's look at our email. We got emails. It was too many for me to parse in here. I don't see any feedback.
I like YouTube comments, everyone. So appreciate YouTube comments.
YouTube comments. There's the easiest. YouTube.com/WordCompleteFM. All right. Well, I think that's going to do it, Frank. What do you think?
I think we had fun. I can't believe we talked about tokens for 30 minutes. We'll see if we can talk about XML for 30 minutes.
There we go. All right. Well, we'll catch up with you next week. So until then, I'm James Montemagno.
And I'm Frank Kruger. Thanks for watching and listening.
Peace.